Welcome to our lecture on sampling distributions. Today, we are going to explore one of the most fascinating and powerful shortcuts in all of statistics, the De-Moivre Laplace Theorem. Imagine trying to calculate the exact probability of getting exactly 5,000 heads in 10,000 coin flips. The math would instantly break a standard calculator. But what if I told you there is a way to turn that impossible counting problem into a simple, smooth curve? Let us dive in and see how this beautiful theorem makes the impossible possible. To begin, let us think about why this theorem matters. When you flip a coin a few times, you can easily use the binomial distribution to find the exact chances of your outcomes. But as the number of trials grows into the thousands, calculating those exact probabilities becomes computationally impossible because the numbers get too massive. This is where the De-Moivre Laplace theorem steps in. It proves a magical property. As the number of trials in a binomial distribution grows larger and larger, the shape of all possible outcomes perfectly transforms into a smooth, predictable, normal bell curve. This means we can use the easy math of continuous curves to estimate the incredibly hard math of counting individual discrete events. Now that we understand the goal, let us look at the mathematical engine behind it. This formula represents the formal conclusion of the De-Moivre Laplace theorem. Conceptually, it tells us that if we take our total number of successes, subtract the expected average, and divide by the standard spread, the result behaves exactly like a standard normal curve as the number of trials approaches infinity. Let us break down the symbols. Xn is our total number of successes. The letter n represents the total number of trials, and p is the probability of success for a single trial. Finally, the Greek letter phi of z represents the cumulative area under a standard normal bell curve. If you increase the number of trials n, the approximation becomes more and more accurate, perfectly matching the smooth curve. This formula we just saw leads us to an important practical question. How do we actually apply a continuous curve to discrete data? There is a fundamental physical mismatch between the two. The binomial distribution is discrete, meaning it only takes whole numbers like 4 or 5 and looks like a bar chart made of chunky, separated rectangular blocks. The normal distribution, however, is continuous, meaning it is a perfectly smooth curve that includes every possible decimal value. When we lay the smooth, continuous curve over the chunky, discrete blocks, the curve cuts right through the middle of the blocks, creating small errors in our area calculations. To fix this mismatch, we must expand our boundaries by half a step in both directions. This adjustment is universally known as the continuity correction. Before we move on, let us see this mismatch with a concrete visual example. Look at the diagram on your screen. The blue rectangular bars represent the discrete binomial distribution, where each bar is centered on a whole number. The smooth red line sweeping over them is our continuous normal approximation. Notice the highlighted orange bar centered at the number 5. If we just calculated the area under the red curve exactly at the number 5, we would only get a tiny sliver of a line. But the actual probability is the entire area of that chunky orange block. To capture that full area using the smooth curve, we have to start at the left edge of the block, which is 4.5, and end at the right edge, which is 5.5. This visual perfectly explains why expanding our boundaries by 0.5 is absolutely necessary. Now that we understand why we need to adjust our boundaries, let us look at the final, highly useful formula that you will use to solve actual problems. Conceptually, this formula takes our target range, applies the continuity correction, and standardizes it so we can look up the answer in a probability table. The letters A and B represent our lower and upper target boundaries. We drop the lower limit A by 0.5 and raise the upper limit B by 0.5. Then we subtract the expected mean, represented by n times p, and divide by the standard deviation, which is the square root of n times p times 1 minus p. If you increase the target range, the difference between the two cumulative areas will grow, representing a higher total probability. Let us put this formula to work with a basic example. Suppose a perfectly fair coin is flipped exactly 100 times in a row. We want to find the probability of getting between 45 and 55 heads, inclusive of both numbers. Calculating this exactly would require using the complex binomial formula 11 separate times. Instead, we will use our approximation. First, we identify our given values. The number of trials, n, is 100, and the probability of success, p, is 0.5. We calculate the expected average by multiplying 100 by 0.5, giving us a center peak of 50. Next, we find the standard deviation by multiplying the trials, the probability of success, and the probability of failure, and taking the square root. This gives us exactly 5. This means a typical result will naturally fluctuate by about 5 heads away from the expected 50. Continuing with our coin flip problem, we now must apply the crucial continuity correction to our target range. Because the binomial distribution uses chunky blocks, the block for 45 actually starts at 44.5, and the block for 55 ends at 55.5. So we expand our lower boundary down by 0.5 and our upper boundary up by 0.5. Now we standardize these corrected boundaries to find their positions on the standard normal curve. For the lower bound, we take 44.5, subtract our expected center of 50, and divide by our standard deviation of 5. This gives us negative 1.1. We repeat the exact same process for our upper boundary of 55.5, which gives us a positive 1.1. Our boundaries are now perfectly standardized. Now for the final steps of this example. We have our standardized boundaries, and we just need to find the area under the standard normal curve between negative 1.1 and positive 1.1. To find the area between these 2 points, we take the total area to the left of our upper boundary and subtract the unwanted area to the left of our lower boundary. Using a standard normal probability table, we look up the value for 1.1 and find 0.8643. We then look up the value for negative 1.1 and find 0.1357. Subtracting these two decimals gives us a final result of 0.7286. Physically, this means there is roughly a 72.86% chance that flipping a coin 100 times will result in between 45 and 55 heads. Let us look at a slightly harder real-world example involving quality control. A factory produces thousands of light bulbs, and historically, 20% of them are defective. A quality inspector randomly samples 400 light bulbs. We want to find the probability that strictly more than 90 bulbs in this sample are defective. First, we identify our parameters. The number of trials, n, is 400, and the probability of a defect, p, is 0.2. Because we are dealing with discrete whole numbers, being strictly greater than 90 is the exact same thing as being greater than or equal to 91. We must rewrite our target this way before doing anything else. Then, we calculate the expected number of defective bulbs by multiplying 400 by 0.2, giving us an expected center peak of 80 defective bulbs. Continuing with our factory example, we next calculate the standard deviation to understand the expected spread. We multiply the 400 trials by the 0.2 chance of a defect and the 0.8 chance of a good bulb. Taking the square root of 64 gives a standard deviation of exactly 8. Now, we apply the continuity correction to our starting boundary of 91. Because we want to include the entire chunky block representing the number 91, we must step back by half a unit, making our corrected lower boundary 90.5. We standardize this boundary by subtracting our expected center of 80 and dividing by our standard deviation of 8. The result is approximately 1.31. We now need to find the probability of getting a standard score greater than 1.31. Let us finish this quality control problem. We need the probability that our standardized score is greater than 1.31. Standard normal tables only give us the area to the left of a number, but we need the area to the right. Because the total area under any probability curve is exactly 1, we can use a simple subtraction trick. We take the total area of 1 and subtract the area to the left of 1.31. We look up the value 1.31 in our table and find the decimal 0.9049. Subtracting this from 1 gives us a final result of 0.0951. Physically, this translates to a percentage. There is only about a 9.51% chance that the inspector will find more than 90 defective bulbs in their sample. Now that we have successfully used this formula in practice, let us understand where it comes from mathematically. To prove why the binomial distribution approaches the normal curve, we must look at its building blocks. We start by defining xn as a binomial random variable with n trials and probability p. The secret to this proof is breaking this complex variable into tiny independent pieces. We can express xn as the sum of n independent Bernoulli random variables, labeled yi. A Bernoulli variable is the simplest possible experiment. It equals 1 for a success and 0 for a failure. By adding these simple experiments together, we build the total count of successes. For a single trial, the expected average outcome is simply the probability of success, p. This sets the foundation for analyzing the entire sum. Continuing with our derivation, we now look at the spread of a single trial. The variance of a single Bernoulli trial is calculated by multiplying the probability of success, p, by the probability of failure, 1 minus p. Because every trial is completely independent, meaning one coin flip does not affect the next, we can simply add their individual averages and variances together to find the totals for the entire experiment. Therefore, the total expected value for xn is just n times the expected value of one trial, giving us n times p. Similarly, the total variance is n times the variance of a single trial, giving us n times p times 1 times p. We have now mathematically established the exact center and spread of our binomial distribution, which we will use in the final step. We have reached the final steps of our derivation. Taking the square root of our total variance gives us the standard deviation, which is the square root of n times p times 1 minus p. Now we apply a process called standardization. We create a new variable, zn, by taking our total successes, subtracting the expected center, and dividing by the standard deviation. This mathematical trick shifts our entire distribution so its center is exactly at 0 and scales its width so the spread is exactly 1. Finally, we apply the broader central limit theorem. It dictates that as the number of independent trials n grows infinitely large, the probability distribution of this standardized sum perfectly converges to the standard normal curve, represented by phi of z. We have successfully proven the De-Moivre Laplace Theorem. We have covered a lot of ground today, so let us summarize the most important ideas. The De-Moivre Laplace Theorem is a powerful tool that proves a discrete binomial distribution smoothly morphs into a continuous normal distribution as the number of trials increases. This allows us to avoid impossible combinatorial calculations and instantly estimate complex probabilities using a simple bell curve. Remember, the process always starts by calculating your expected mean and standard deviation. And most importantly, never forget to apply the continuity correction by shifting your target boundaries by 0.5. This perfectly accounts for the physical difference between chunky probability bars and a smooth curve. You now have the mathematical backbone to handle large-scale probability problems with confidence.